Okay, welcome back. We just got done talking about our equations of lines and we refreshed our memory a little bit on what it meant to have the equation of a line and that what that had to do with our statistics we'll see here in a moment, right? Equations of lines were the ones where we had a slope and a y-intercept and we wanted to figure out what the relationship between x and y meant. And so that right, what we want to do is we want to say, well, okay, now that we have that, what has that got to do with our statistics? Well, what we want to do is we want to talk about a new kind of graph. And the one we're going to be talking about is one that we can build something called a regression equation based on what's called a scatter plot. Well, what's a scatter plot? A scatter plot is a graph. So this is another graph kind of related to what we were talking about back in chapter 2, where the graph of the data from two quantitative variables of a population, and in the scatter plot we use the horizontal axis for observations of one variable and the vertical axis for observations of the other, and each pair of observations is then plotted as a single point. So in other words, these pairs are numbers that go together, right? So when x is one value, y is another value, and there's pairs of values that go together in our data, right? So this has to be the kind of data set where one observation goes with another observation. Say, if we're talking about height versus weight, right? And we had a data set where for one subject, that subject had a height and that subject had a weight. If we looked at all the subjects' heights and weights and put them together, we could say, well, maybe there's a relationship between the height of the person and the weight of the person, right? And those variables would go together. Well, let me show you an example of one that, really small example, and we're going to do this with a very teeny tiny little data set right here just to illustrate our points, but we can extend this to larger data sets as well. All right, so we did a real brief study, let's say, and the hours slept at night and their happy mood in this fictional data set is given in the table, right? So we talked about each subject, and each subject slept, they give how many hours they slept last night, and then they rated their mood. And it looks like the mood was rated from, let's see, from 0, probably from 1 till 7 or something like that, 1 to 8 maybe, and then the hours slept, well, they give the hours slept, right? Full hours we're going with, not half of an hour or anything like that. So let's say in this example, somebody who slept 7 hours said they had a happy mood of 4. Well, somebody who had 5 hours had a happy mood of 2. Yeah, I can see being kind of grumpy after 5 hours. Somebody had an 8-hour sleep and they had a 7 for their happy mood, so they seem pretty happy, I guess. But somebody slept 6 hours and had a mood of 2. And 6 hours, somebody else who also had a 6-hour sleep, but this time they have a happier mood of 3, maybe. And somebody has slept 10 hours, well, they seem a little more grumpy than the guy who slept 8. I don't know what's going on with that. But anyways, this was our happy mood chart. So what do? Well, let me show you a scatter plot. Along one axis, we talked about the hours that were slept. Here they are. So we put our hours slept last night along the horizontal axis. And then we put our mood. And we're going from 0 to 8 right here. Nobody said they had a mood of 0. I guess that would be just smashingly bad, I suppose. But somebody had a mood of 7 was pretty good. And so we trace that. And this is our scatter plot, right? The scatter plot says that the person who slept 5 hours had a happy mood of 2, while the person who slept 10 hours had a happy mood of 6, right? And all we're doing is we're just plotting each one of these points. 8 hours gave this guy a 7, which was pretty good, I guess. I suppose if I got 8 hours a night, I might be a 7 too, depending on the day. So what could we tell about this data? Right? Just sort of an interesting. Is there a pattern? Well, most definitely, right? It looks like the pattern goes, even though, the numbers vary down here in this table a little bit, it looks like there's definitely some kind of pattern in this scatter plot, right? It looks like that if you get an increasing amount of sleep, in general, even though it's not specifically always the case in this table, it appears you get a better, happier mood. Well, that would seem to make sense to us. A happier mood is associated with more sleep. why not, right? So that's pretty good. That gives us an idea of what that means, right? And if we think about what kind of pattern we're looking at, well, if it's almost as if we could draw a line down the center of these points in such a way that, well, the points kind of fall evenly, more or less, on either side of that line. If we could draw a line that somehow shot right down the middle, however we define that, of those points, well, yeah, sure enough, we would have what was called a best fit line. Well, that best fit line, in this case, is actually going to be what we call our linear regression. So I'm going to show you guys how we can do a linear regression using Excel. I'm going to tell you that in this chapter we're not going to do some manual calculations because they're really very heavy and time consuming. What we're going to do is we're just going to go through and use Excel to compile some of this. So I'm going to illustrate how do we actually get the equation of that line. How could we figure out what B0 and B1 were so that we could use it to, maybe within our data set, the type of data that we're talking about, predict what would happen if we got X number of hours per sleep, right? We could get Y as our mood and say, well, what should our mood be if we get this many hours of sleep? And that would be kind of good to have, right? That's a numerical balance that we can find in our statistical data, which is kind of cool. All right. So what do? We're going to use something called a least squares criterion. And basically what this says is that the line that fits best in our data points is one that has the smallest possible sum of squared errors. Sum of squared errors. Have we seen something about that? Well, you betcha. Last week we talked about a sum of squares when we were taking our standard deviation. You recall that, right? When we had our standard deviation of a variable x, what we did was we took the difference between each x value and the average x value, and then we squared those values and we summed it up, and that was a sum of squares. And that gave us a positive value that could give us the average deviation. Well, in a way, that's kind of what we're doing right here. And with that least squares criterion, we're going to get a regression line and a regression equation based on these least squares criterion. In other words, what our goal here is to come up with an equation of a line that gives us the smallest possible least squares differences between the mean and the variable. So what does that mean for us? Well, the notation that we're going to use right here, we're going to say, well, what we call the sum of squares errors are defined on whether we're talking about the x variable, whether we're talking about the y variable, or whether we're talking about mixing the x and the y variable. So don't worry so much about this one. If we're computing in the formula, I guess this is sort of the way to do it. Right here, if we're using Excel, this middle column is actually a really easy one to use, and this is going to be my defining formula for the Excel spreadsheet, and I'm going to show you how this is done. But basically the way it works is this. The formula says B1, that is our slope, is going to be equal to the sum of squares difference of our mixed x and y variable and the sum of squares of our x variables. B0 is going to be our mean y value minus B1 times our mean x value. All right. Well, I'm going to show you how that works here, but so that you see it, let's say that we were taking one point right here, this particular xy point. What we're saying is that for every single value, right, if I were to go for my happy mood versus hours slept last night, the average happy mood was a 4, the average hours slept last night was 7, so if we took the difference between our x coordinate here on this particular mood of 10 minus our variable, right, of y, right, that would be this difference. We call that difference our y, our difference in x, so if we square that, that's our square for that particular point. And then y minus y bar is our difference right here, and we're going to take that and square it. And if we take the sum of these squares of these differences right here and add them all up, right, when we divide the mix of the sxx and the sxy divided by SXX, right, we're going to get that sum. I mean, it's sort of weird to talk about right here, but let's do it on I'll show you how I come up with this chart and we can come up with the equation. So what I'm going to do is I'm going to go to Excel and I'm going to show you how this is done. So here is my Excel spreadsheet, and basically what I'm looking for is I'm looking for my difference between y and the y bar. Well, we need x bar and y bar right here. So remember that was how we found the mean, equals average. So we're going to get the average x right here. Boom, there it is. So we're going to call this x bar. And then we're going to get our average y, right? So we're going to get our average y. So we just copy this formula over. There it is. Nope. Let's try that again, Professor Peoples. No, it doesn't like that. Grab the corner, scooch it over. There it is, right? So this is our y bar. All right, so our y bar is 4. So what we're going to do is we're going to take the difference between each x value. So the difference between x minus x bar, which is 7. And we're going to get the difference for each one of these variables, right? So these are all of our x minus x bars right here. And we do the same thing for our y's. We're going to take y, the y value here in column B, minus our y bar of 4. Boom, there it is. And then we copy that all down. There. Okay. The next is to square each of our x minus x bars. So I'm going to take the value that I get from C and I'm going to square it. That's what it looks like when we square in Excel. And we copy that on down. Boom. We're going to, this variable right here, when we take the sum of this, if we take the sum of all of these squares, we call this variable SXX. All right. Then we're going to do a similar thing right here, only this time what we're going to do is we're going to take the product of what we have in column C times, we use the asterisk to do that, what's in column D, and get that particular product. And we copy that all the way down. Boom, there it is. So if we take this sum, we're going to get the variable SXY. And then finally, we're going to get the square of all of this. But, well, actually, right now, we could work this out, right? We could work out what our slope was, right? We said that B1 was equal to SXY divided by SXX, right? That was the formula in our screen. So what we're going to do is we're going to take our slope, right, SXY, and divide it by SXX. And that's our slope of our line, right? Next, if we wanted to get B0, we said that B0 was going to be equal to our y bar, right? So y bar, not var, minus B1 times our x bar. Right? And that was the formula right here. So let's do that. When we take the value from y bar, which is 4, we subtract from that the value of our B1 times our x bar, 7. Boom. This is our y-intercept. So our equation based on this will be y equals -3 plus 1x. And that is our best fit linear equation. Right? Equation B0 minus plus B1 times x. Well, let me see. Let me just make sure I've got that correct in my spreadsheet here. B0 y bar plus, right? It was y bar plus. I guess I should be very careful right here. Y bar plus. No, it was y bar minus, right? Let's go back. Let me just verify this. Let's go back to our slide right here. Our slide said it should be y bar minus b1 x bar. Yeah, there it is. Okay, so that was our formula right here. Boom, that's the one I'm using. So, okay, yes, that makes sense. All right, so this was the equation that I got on my sheet, right? Y minus, so what does that mean for us? Well, if we actually look at this description, oops, let me go to my equation right here. Oh, too far ahead. Okay, so if I go to my equation right here, my line, my best fit line, I'm telling you that this equation right here would have the equation of y would equal -3 plus 1 times x. And so the slope of this here would work right. And any point that we got on here, we could predict using this equation. All right, there we go. So this is how we might get a best fit line using what we call a linear regression. Now, there are a couple of other examples here real quick. Let me just wrap this up. If we had a larger data set, we could go through and do exactly the same thing with our least squares criteria. Here's an example where if we had a bunch of points in our scatter plot and we got a best fit line, we see that we have y hat. Y hat is what we're going to use right here, this variable right here with the y and it looks like a little hat over it. Y hat is going to be our variable describing the predicted y. So if I were to go back to my screen, I probably should make an adjustment right here. This isn't y. This predicted y is going to be y hat. Right? So we call that y hat. All right, so y hat is the predicted value of this line. Now, a couple of things we have to look out for. There's something called a response variable and a predictor variable. The response variable is the variable that's measured or observed, right? The predictor variable is the variable used to predict or explain the response values. So we use this linear regression to make predictions in either one of these, and when we do that, if we go beyond our data set, that's called an extrapolation. So if we go less than our variables, less than what values in there, we are extrapolating. Okay. The y hat, right? Y hat is our predictor variable. The x is our predictor variable. And the y hat is our response variable, right? Okay. So in other words, there are some differences that we could get. For example, if we get points that are like way off, they could influence the way this line is, right? And we call that an influential observation because if we took it away, we might get a different response right here, right? So we see this line in yellow that could be changed by having an influential observation. Okay. So what we want to do is we want to make sure that our that if we're going to find a linear regression, the regression line for our data points, we're going to draw a scatter plot, and if the data points do not appear to be scattered about the line, they really don't determine a regression line. Okay, so that's a fact that we're going to have to look at here shortly. Okay, more to come.